In section 2, we're going to talk about solving systems of equations using substitution and elimination. So we've already talked about how to solve a system of equations by graphing. And when we do that, we're looking for the intersection of those two lines. So now we're going to talk about how to solve a system of equations algebraically, so without using a graph. So we're trying to find an ordered pair that works in both of our equations. So the first method is solving systems of equations by substitution. So there are 4 steps. The first step is to solve one equation for one of the variables. So you need to either have x equals or y equals for one of your equations. Now, this step may already be done for you depending on what the equations look like when they're originally set up. Secondly, you're going to now substitute that expression for the variable found in step 1 into the other equation. Then the third step, solve that equation for that first variables, and then for the last step, find the value of your other variable by plugging in the solution found in step 3 into one of the original equations. So let's go ahead and look at some examples. So our first example, we have y equals negative 3x plus 4 and y equals 3x minus 2. So in this case, both of our equations are already isolated as x equals or y equals. So I can just pick one of my equations to plug in for the y and the other, and it doesn't matter which one. So I'm going to take the negative 3x plus 4 and plug it in for the y in my second equation. So I get negative 3x plus 4 equals 3x minus 2. And now I'm just solving a linear equation. So I'm going to add 3x to both sides. So we get 4 equals 6x minus 2. Now I'm going to add 2 to both sides. So we get 6 equals 6x. Divide both sides by 6, and we get that x equals 1. Okay. Now I want to plug that value for x into one of my original 2 equations to solve for y. And I'm going to go ahead and plug it into the second equation. So 3 times 1 minus 2. 3 times 1 is 3, so we get 3 minus 2, which means y is 1. You are allowed to leave your answer as x equals y equals. You aren't required to write it as a coordinate, but if you do, remember it's always x comma y. So in this case, that would be 1 comma 1. And just make sure you remember to put your parentheses because it's a point. Our second example has x plus 7y equals 0 and 2x minus 8y equals 22. So when you have a system and one of the variables isn't already isolated and you're trying to figure out which variable do I isolate in which equation, I always look for a variable that's already just x or y and get it by itself. So in my first equation, I have an x. So I'm going to get that by itself by subtracting 7y from both sides. And we end up with x equals negative 7y because 0 minus 7y is negative 7y. I'm now going to take this negative 7y and plug it in for x in my second equation. So we get 2 times negative 7y minus 8y equals 22. 2 times negative 7 is negative 14. Negative 14y minus 8y is negative 22y. We're going to divide both sides by negative 22, and we get y equals negative 1. And since I already isolated my x variable in my first equation, it's easy enough to just plug that in to that isolated equation to solve for x. So x equals negative 7 times negative 1, which means x is 7. Which as a point would be 7 comma negative 1. In our third example, we have 6x minus 12y equals 24, negative x minus 6y equals 4. So when I'm trying to figure out which equation I'm going to isolate, I'm going to go with the second one because I have an x that is got a -1 in front of it, which is a lot easier to deal with than my first equation where I have a 6 and a -12. So my first step is going to be to add 6y to both sides. We get -x equals 6y plus 4. And then I have to get rid of that -1 by dividing everything. So we end up with x equals -6y minus 4. So we're now going to take that expression and plug it in for x in my first equation. So we have 6 times -6y minus 4 minus 12y equals 24. Next, I'm going to distribute that 6 into my parentheses. So we get -36y minus 24, and then minus 12y equals 24. Combining like terms, we get -48y minus 24 equals 24. Add 24 to both sides. We get -48y equals 48. Divide both sides by -48, and we get y equals -1. So now to solve for x, I'm going to go ahead and plug that into my isolated equation. So -6 times -1 minus 4. So we get 6 minus 4, which means x is 2. So as a point, that is 2 comma -1. In our last example, we have 1/2 x minus y equals 3 and 6x plus 6y equals 0. So even though I have a y, that's a -1 in my first equation, I also have a fraction in that first equation. And my second equation, both of the numbers in front of x and y are both 6's, so it's actually not going to be too difficult to solve for x or y in that second equation, which is what I'm going to do. So I'm going to solve for y. So I'm going to subtract 6x from both sides. So we get 6y equals -6x. Divide both sides by 6. And we get that y equals -x. So I can now take this -x, plug it in for y in my first equation. So we have 1/2 x minus -x equals 3. So it's important here that you remember the minus and the negative, because x is negative and there's already a subtraction sign. So we get 1/2 x plus x equals 3. Now when I do 1/2 x plus x, you can think of that x in front of the 1 in front of the x as 2 over 2. So I'm doing 1/2 plus 2 over 2, which is going to give us 3/2 x equals 3. Now I want to get rid of the 2 from both sides, so we're going to multiply both sides by 2. So we get 3x equals 6, and then we'll divide both sides by 3, and we get that x is 2. And then for y is just -x, so y equals -2. So we get 2 comma -2. And the nice thing about solving a system of equations algebraically is you can always check your answer by substituting the values you got for x and y into your system of equations and make sure both equations are true. Or you can graph both equations and see that the graphs also result in the same solution. So our second method is going to be elimination. So sometimes substitution is difficult due to fractions. Like that last example that we just saw had that 1/2 in front of x. So in that case, elimination might be the better choice because then you can get rid of the fractions and not have to deal with it. So when you're solving a system of equations by elimination, the first step is to make sure each equation is written in standard form. So what that means is your variables x and y have to be on the same side, and your constant has to be on a side by itself. And similar to elimination, substitution, this step may already be done for you. You may not have to rewrite an equation. Step 2 is probably the most important step when it comes to elimination, and that's figuring out what you're going to multiply one or both of the equations by in order to eliminate a variable. So you have to multiply one or both of the equations by a number to make sure that the coefficient of one of your variables in both equations is the same but with opposite signs. So you have to have one positive and one negative, and they have to have the same number in front of that variable. Once you do step 2, you add the equations together and it eliminates that variable you chose. Solve for the variable that remains, and then plug in that value into one of the original equations to solve for the second variable. So the steps, especially step 2, kind of sounds a little bit confusing when you're looking at it. So we'll talk about it using some examples. So our first example, 4x minus 3y equals 4. 2x plus y equals negative 8. So both of my equations already in standard form. So now I have to ask myself, which variable do I want to eliminate? So there's 2 things I look for when I'm trying to decide which variable to eliminate. One, I check to see if one variable is easier to eliminate than the other. So that would mean, can I eliminate a variable with only multiplying one equation? So is there a variable that's got a 1 in front of it already? Secondly, is can I avoid multiplying by a negative? So is there a variable that already has opposite signs? Now sometimes both of these things are true for the same variable, sometimes they're not. And in that case, I typically try to go with, are the variables already opposite signs? That way I can avoid multiplying by a negative. So in this case, 2 and 4, it is easy enough to make a 2 of 4. But I would have to multiply by a negative in order to get them to eliminate. If I look at my y's, I already have one positive and one negative y, and I can easily make that one y a 3. So I'm going to eliminate y by multiplying the entirety of the second equation by 3. So we get 4x minus 3y equals 4. And our second equation becomes 6x plus 3y equals negative 24. So everything gets multiplied by the 3. We add our equations together, and the negative 3y and the positive 3y cancel. We get 10x equals negative 20. Divide both sides by 10, and we get x equals negative 2. Now that I know x, I go back to one of the original 2 equations to plug it in to solve for y. Again, I try to avoid negatives when I can here, so I'm going to plug it into the second equation because y is just already a 1y. So we have 2 times negative 2 plus y equals negative 8. So 2 times negative 2 is negative 4. And then we will add 4 to both sides. And we get that y equals negative 4. So as a point, that is negative 2 comma negative 4. So I find elimination to be a little bit easier. It definitely is less time consuming than substitution, but some people find it a little bit more difficult. In our second example, we have 2x minus y equals negative 1, and then 3x equals 30 plus 2y. So in this case, my equations are not both in standard form already, which means I need to get my y from my second equation on the same side as the x. So I'm going to do that by adding 2y to both sides. So my first equation doesn't change, 2x minus y equals negative 1. My second equation becomes 3x plus 2y equals 30. So in this case, I'm not going to try to eliminate x because in order to make 2 and 3 the same number, I'd have to multiply both equations. And I try to avoid multiplying both equations if possible. My y's already opposite signs and one of them is a 1y, So I can easily make that first equation have a 2y by multiplying everything by 2. So we get 4x minus 2y equals negative 2. Second equation stays 3x plus 2y equals 30. You add the equations together, the y's cancel, so we get 7x equals 28. Divide both sides by 7, and x equals 4. And it does not matter which equation I plug that x in to solve for y. And in this case, both of my equations have a negative in front of the y. So I'm going to choose the equation with smaller numbers to plug it back into. So I'm going to use the first one. So 2 times 4 minus y equals negative 1. So we get 8 minus y equals negative 1. We're going to subtract 8 from both sides. So we get negative y equals negative 9, and then we have to get rid of the negative by dividing both sides by negative 1, and we get y equals 9. So as a point, it's 4, 9. So for our last example, we have x plus 2y equals 4, and 2x minus 3y equals 1. So in this case, my y's already have opposite signs, but I'd have to multiply both equations to eliminate y. My x's not the same sign, but I can easily make a 1x a negative 2x by multiplying that first equation by negative 2. So even though I'm multiplying by negative, it's better than multiplying both equations. So we get negative 2x minus 4y equals negative 8. Second equation stays 2x minus 3y equals 1. So we add the equations together. The x's cancel. We get negative 7y equals negative 7. Divide both sides by negative 7. We get y equals 1. And when it comes to choosing which equation to plug that in, I'm going to choose the first equation because, again, no negatives. So we get x plus 2 times 1 equals 4. So x plus 2 equals 4. Then we're going to subtract 2 from both sides, and we get x equals 2, which as a point is 2, 1. The last thing we need to discuss is how can you tell algebraically whether a system of equations has no solution or infinitely many solutions. In both cases, the decision is made when both variables are eliminated. So the first one we'll talk about is if you end up with a true statement. When that happens, we have infinitely many solutions. So a true statement could be 0 equals 0. You could get 4 equals 4, or you get something like negative 9 equals negative 9. So it's not required to be 0 equals 0, although that is the most common solution. It is not the only one you could get. The second one happens if you end up with a false statement. And that is when you have no solution. So that could be 0 equals 4, 4 equals negative 9, or like 0 equals negative 9. None of these are true statements, which means there is no solution. 0 equaling another number is the most common type as well, but it is not the only time you could see. So if you end up with no variables left, then that's when you'll have a no solution or an infinitely many solutions. Now, when we say no variables, we do mean no variables. X, if you have X or Y and a 0, that does not mean the variables are eliminated. You can have 0 as a solution for one of your variables. So just make sure that you are checking to see that you no longer have a variable before saying there's infinitely many or no solution. Let me know if you have any questions about solving by substitution or elimination, or determining if you have infinitely many solutions or no solution.